Now, section 4.5 with these moments timer questions where we have a very familiar setup. We've got a support at C, a support at D, often labelled at ends of the rod A and B. We've got a rod. It can be a uniform rod or it can be a non-uniform rod. But in these questions, they're going to add in one more thing, which is this idea of tilting. It's on the point of tilting. Well, by chance, I just seem to have drawn my rod so it's not in contact with C there. So let me just try and draw a slightly neater one. Now, I'm not going to go through any full examples here, I think. Let's just get the idea of what's happening here. When a rigid body is on the point of tilting about a pivot, what we get is that we can ignore one of the reaction forces. So let's just, what would happen here? There'd be a force acting downwards, which would be the rate of the rod. There'd be a force acting upwards here and here, which would be our reaction forces from our two supports. Now, if I were to push down on this side here, okay, then what would happen? If I pushed hard enough, then this whole thing would spring up into the air and start rotating that way, wouldn't it, if I pushed hard enough? Now, as I push down a bit here, if I don't push hard enough, this thing isn't moving yet, it stays in equilibrium. But I've put a force on here. Can you imagine that? If there's a big heavy beam, if there's a bit of a force on here, but not big enough to make it move, you have put a force on here. So can you see that this force here can't stay the same? Well, why not? Well, because this force here is the weight. That has to stay the same. That's not going to change. The mass of this beam isn't going to change just because I push down on one end of it. But if I push down on here, then I'm increasing the clockwise moment. Okay? So if I'm increasing the clockwise moment here, there are two ways that this beam could stay in equilibrium. One is if somewhere else the clockwise moment decreases, and the other way would be if the anti-clockwise moment increases. So if I push down on this beam and somebody else pushes down on this side, then that's increasing the anti-clockwise moment, but that's not happening. What's happening is I've got a big heavy beam, I'm pushing on this but not hard enough to move it. Well, in that case, what must happen is the reaction force at D decreases. Now the way to see that is imagine you are, this is a support here, and this isn't a support, this is you standing underneath, holding it up. If you're standing underneath this big heavy beam holding it up, you're having to push quite hard to keep this thing from falling down. If somebody comes and pushes on this end, even if they don't push hard enough to take this beam off your hands, they are making your load lighter, aren't they? So your reaction force is going to decrease when there's a bit of a force here. Now, when we say we're talking about tilting, these questions are a limiting equilibrium situation, or on the point of tilting is a phrase that we see a lot. And when we say on the point of tilting, what we mean is that we've put the forces in there. So we've got a reaction here at C, we've got the weight acting down here, we maybe have a force acting here, or maybe we have a force over here pushing upwards. But the reaction here at D vanishes. So we've pushed so hard here that there is no reaction at D. If I took the support away at D, this thing wouldn't move still. Okay, so although this thing might still be touching point D, it's only just touching it and there is no reaction force. That's what happens when a point is on the point of tilting. When you hear that phrase, on the point of tilting, it means basically you can ignore one of the reaction forces. Okay? And if you look at the question, if you look at where the forces are, you can ignore one of the reactions. Now, once you've done that, if you go through the same method that we've done in the rest of the chapter for upwards forces equals downwards forces, moments clockwise equals anti-clockwise moments. Obviously, in this case, we would take moments around this point now. That's where I would suggest we take moments. You don't have to, though. You can take moments around any, point A or point B or wherever you fancy. You can even take moments about D if you want. It seems a bit weird because this thing is actually turning around here. So intuitively, this is the point around which we're turning. So to me, this seems to be the obvious place to take moments. But you've got two methods. Resolve upwards forces equals downwards forces. Take moments about a point. Clockwise moments equals anti-clockwise moments. From that, you get two equations rather, and you can solve those two equations together simultaneously. Now, I'm not going to go through the examples because once you've drawn the diagram and you've taken out that force there, you've got a diagram that looks just like it did before. If you don't understand the methods for taking moments here, go back and look at some of the examples from the previous videos in this chapter and get into the habit of it. And once you get there, then if you can draw the diagram, the method from there is exactly the same as it was previously. So that's everything on the moments chapter. I hope that helps. Good luck.